Hello everyone, welcome back to another YouTube video. So today we are solving another very interesting problem which is called the three-sum problem. So this particular problem has been asked at various companies in various interviews. So let's dive deep into it. So we have an integer nums where we have to return all the triplets nums I, nums j, nums k such that I not equal to j, I not equal to k and j not equal to k and nums I plus nums j plus nums k must be equal to 0. We also notice that the solution set must not contain duplicate triplets. Okay. So basically, from this particular array, we have to figure out a particular triplet or a set of triplets, let's say, which sums up to 0, and the resultant array should not contain any duplicate triplets. Understood. So just by looking at the problem, the first solution that strikes my mind is having three nested loops so that we can figure out every possible triplet which sums up to 0, and then we can have a set to store these triplets so that we get rid of the duplicate entries then and there. So, but this particular solution is n cube of time complexity. So, this is not something we want to do in interviews. So, let's look into a much better approach and a optimized one. So, let's say we have three entries here for the triplet, 1, 2, and 3, and we need to add these and figure out if the solution, if the summation is equal to 0. So, okay, so let's first sort this array and let's understand why sorting this array makes a difference. So, after sorting, this comes up to be minus 4, minus 1, 0, 1, and 2. So, as we can see here, that after sorting this array, we all will always have duplicates grouped. Like we have, sorry, we will have the duplicates grouped here. So, let's say whenever we are starting to sum, we keep the first element, for let's say minus 4, as constant. Like for the first iteration, we will not be changing the minus 4 here. We will keep it as it is, and then we'll reduce the sample space to from L to R, which is our left and right pointer. So basically, we'll have two pointers here, left and right, which will work and figure out the other two, which can possibly land here, and the entire sum here should be equal to 0. So let's see how we can achieve this. So minus 4 is constant. Let's for now say that the constant value is a. For the first iteration, we'll keep minus 4 constant in here. We'll figure out what next two elements we need to add here. So let's see. So minus 1 and 2. Minus 1 and 2. Yeah. So this particular solution comes out to be minus 3. So the sum is less than 0. So we want the sum to be greater than 0. So we'll move the left pointer towards right. Now, why are we moving the left pointer and not the right pointer? It is understood that the array is now sorted. So if we want the sum to be greater, we want a larger number to be added here and not a lesser number. So for moving to a larger number, we'll move the left pointer because moving the right pointer will give us a smaller number. So moving the left pointer makes more sense. But now, as we can see here, we have encountered a duplicate. We already have added minus 4, minus 1, and 2, and we figured out that it is equal to minus 3, and the sum is less than 0. So we don't want to recompute this. So what we'll do is we'll simply shift the left pointer again so that now we have minus 4, 0, and 2. So I'll change it to 0. So now our solution is equal to minus 2. So which is again sum is less than 0. So I'll move the left pointer again. So now I'll update this to 1. This time we have the solution as minus 1. And now the left pointer coincides with the right pointer, which is not suitable for our case because we need two different numbers to stand here, as we have I should not be equal to j, I not equal to k, and j not equal to k. So this is not a suitable scenario. So this time we will shift the a variable, like we'll move to the next element, which is -1 in this case. So what if this was -4 again? So if it was -4 again, then we would have moved to the next element, which is -1 in this case. Let's assume if we had -4 here and not -1, so we would have moved the pointer a from -4 to -1, because for -1 we have already computed all possible options and we didn't get the solution to be 0 anywhere. So now what happens is, whenever if the sum is greater than 0, in that case, let's say here, if the sum is greater than 0, then we will always shift the right pointer, because this time we want our solution to be lesser, like the sum to be lesser and more closer to 0. So we'll move the right pointer. And let's look at how this will happen for this window. Now the -1, it changes to -4, changes to -1, and the window is now between -1 to 2. Now, since -1 remains constant, we can recompute -1 for sure. So we have -1 and 2. So this time, -1 plus -1 and 2 is equal to 0. So we have found our first triplet, and we can simply add it to our resultant array. So this way we can figure out all possible triplets which accounts to 0, and we have where we have sum is less than 0, so we'll simply move the left pointer. And if we have sum greater than 0, we'll move the right pointer to make sure that the sum is more closer to 0 this time. And if the sum is 0, like in this case, we'll simply add it to the resultant set. So this is the entire approach. So looking at the time complexity, so the time complexity will be big O of n log n for sorting, and then another n square for the two-pointer approach we are doing. So the resultant time complexity will be equal to n square, which is much better than n cube, like a previous approach. And for the space complexity, it will be equal to big O of 1 if we ignore the resultant space that we are using. So now let's move to the code. So now we have the function defined here, which takes the array nums. Then we'll sort the array as said, just to make sure and the handling of duplicates is easier. We initialize the resultant array to store the triplets. Then we'll first iterate through the array and fix the first element. Like we were having that particular a that we were fixing for every iteration. So this time we fix it, and in any case, if num size greater than 0, we break immediately, because then there is no need to compute, because no triplet will can sum to 0, because the entire array is now sorted and the first element itself is greater than 0. So, and we will be skipping duplicates. If any nums I will is equal to nums I -1, so we'll keep continue until we find a unique number to start our iteration with. So then now we define the two pointers for the two pointers approach. The left will be equal to one left to the number we are fixing, and the right will be the last possible number in the array. Then we'll use the two pointer approach to find the two numbers that sum to minus nums of I, so that we have a 0 output. So while left is less than right, as we were doing, so integer sums we are making it equal to nums I plus nums left plus nums right. If sum is greater than 0, we're shifting the right pointer. If sum is less than 0, we're shifting the left pointer. Sum is greater than 0, then shifting to the right pointer. Else, if we have found a valid triplet, then we'll add it to the resultant vector. If not, we'll move the left and the right pointer and keep doing it until we find a suitable triplet to store. So we have to make sure that we are skipping any elements in the left and right pointer zone as well. So we have here, like, while left is less than right and nums left is equal to nums left -1, so we'll increment the left pointer until we find a unique number. So we'll return the result with all the unique triplets. So this is the entire solution of the problem. I hope you enjoyed this particular solution. Make sure to like the video if you enjoyed it, and please drop any next question you want to see in the coming videos as well. Thank you so much.